Welcome to Landscape Irrigation Week 3. This week we'll be talking about the Rainbird Chapter 4, Determining Water and Power Supply. Rainbird Chapter 4 covers pages 26 through 31. The information gathered on a landscape site plays an important role. The needed data includes static water pressure, water meter size, service line length, and the type of the service line pipe. Here we have an example of some of the products that you might use to determine your static water pressure. Here we have a system where we have a pressure gauge hooked up to a hose bib. There's also this dynamic flow gauge that you can purchase where you can get your static water pressure by turning off this valve, hooking it up to your hose bib, and reading what your pressure reading is. Then if you'd like to see what your dynamic pressure is at a given flow rate, you open up this gate valve and you read to see what this says here as far as flow and compare it to the PSI on the right. So if you need a certain amount of pressure to operate your system, you're going to want to make sure that you dial it in on the right side with a little bit of a cushion and then see what you have to work with on the left side. That can help save a little bit of time. And then when you go to check out your meter, you want to make sure that you figure out what size it is. And then if you're not sure about your service line type size, there are tricks that you can use to determine that. So what size is your meter? Usually you can tell because it's stamped somewhere on the inlet of the tailpiece of the meter. And if you can't find it there, then sometimes it's printed inside of this register here, and that might be where you might find it. So now here's a chart that you can find inside of the Rainbird text, but I wanted to point out a couple of things specifically here. And what this chart is about here is telling you what size pipe you have in the ground if you're not sure what size pipe it is, but you wrap a string around it and then you measure the string. So this chart is fairly accurate as far as the length of the string is somewhere around 2 3/4 inches for a 3/4 inch copper line. And then also 3.5 inches for a 1 inch copper line, 4 3/8 for 1 1/4. And then for galvanized pipe, 3 1/4 inch is approximately a 3/4 inch galvanized line, and a 4 inch string would be a 1 inch, and 5 inch would be 1 1/4. So what I wanted to point out here is that they only offer those two sizes on this chart, and one would be this copper pipe here, and what they're talking about is the outside diameter right here of copper pipe. So if you take this string 2 3/4 and you divide it by 3.14 or pi, you're going to end up with a number that looks very close to this right here. So that's basically what they're doing for you in this chart, but it's more likely that you're going to remember pi, 3.14, then you're going to remember where you put this chart. So just keep that in mind. And one little trick is to carry some dental floss in your truck because it doesn't stretch, and it's something that is easy to carry around, and it's lightweight, and it'll slip underneath pipes a lot easier than trying to find some other type of rope or something else like that. The other thing I wanted to point out is that because they only have galvanized and copper on here, is to point out that the OD for standard steel pipe or galvanized pipe is going to be the same OD for plastic pipe. So it isn't that they didn't forget it, it's that it's not needed because they're both the same, but it's not pointed out real great in the manual that way. In the Rainbird Landscape Design Manual, they list 3 rules for determining an appropriate flow maximum for your design. Rule number 1, the pressure loss through the water meter should not exceed 10% of the minimum static water pressure available in the city main. Rule number 2, the maximum flow through the meter for irrigation should not exceed 75% of the maximum safe flow of the meter. Rule number 3, the velocity of flow through the service line should not exceed 5 to 7.5 feet per second. So we're going to break these down one at a time, and then we're going to see which of the three rules are the most restrictive, and that's the one that we'll use to determine the flow maximum for our design. So rule number 1, the pressure loss for the water meter should not exceed 10% of the minimum static water pressure available at the city main. So in the illustration that we're provided in the landscape manual, it shows in figure 19 that we have 111 psi out of the street. So if we have 111 psi, to determine what our 10% maximum loss is, we take 111 psi, multiply it times 0.10 and come up with 11.1 psi as an acceptable amount of loss maximum for this system. So what we want to do is take a look at the water meter friction loss chart and see how much water pressure we're going to lose going through this meter. So because rule number 1 says that we can't lose more than 10%, we know that we can't lose more than 11 psi, so let's see what flow rate that is. So it looks like without going over 11 psi, that flow rate is going to be 24 gallons a minute, and our loss will be 9.5 psi. So for rule number 1, the flow rate is going to be 24 gallons a minute. Rule number 2, the maximum flow through the meter for irrigation should not exceed 75% of the maximum safe flow of the meter. So how we're going to do that is we're going to look at the maximum flow listed and multiply that number times 0.75 to get to the 75% of the meter flow threshold. So here is the meter that we're going to be using as a 3/4 inch, and they list the maximum as 30 gallons a minute. Well, we can only use 75% of that, so we would take 30, multiply it times 0.75, and end up with 22 gallons per minute. So here we have 22 gallons per minute, and our loss is 7.9 psi. So keep that in mind. Rule number 3, the velocity of flow through the service line should not exceed 5 to 7.5 feet per second. This is similar to the rule of 5 feet per second that we covered in Chapter 1. If you remember, we talked about the industry standard of 5 feet per second being the maximum flow through PVC pipe. And on this friction loss chart, you can see the gray area where it steps down is where 5 feet per second takes place. So avoiding staying out of that area is a good practice because it can help save the life of the components of your system and also help avoid water hammer. But when it comes to water meters, that's not always the most practical way to do it. So what they're going to do is make an exception here for 7.5 feet per second for the flow of the water meter. So in this chart, in the book, they originally talk about 3/4 inch pipe. So what we're going to be doing is looking at 3/4 inch pipe here, and using this 7.5 feet per second rule, we're going to look at the velocity column and find a number that falls under 7.5, and that happens to be right here. And in this case, it leads to 10 gallons per minute. So remember that number. Okay, so now going back over the 3 rules and the limits that they set on us and the flow rates that we came up with. So rule number 1 limited the system to a maximum of 11 psi loss through the meter, so we were limited to 24 gallons a minute. Then rule number 2 limited us to 22 gallons a minute, which would result in a loss of 7.9 psi. Rule number 3 limited us to the 7.5 feet per second in copper tubing, which led us to 10 gallons per minute. So now we have to choose the most restrictive of the 3 rules, which would be the least amount of flow. So it looks like rule number 3, 7.5 feet per second, copper tubing, 10 gallons per minute. Okay, so now we should be able to move along and figure out what our dynamic pressure is going to be. But before we do that, we need to figure out how are we going to calculate friction losses through fittings. And the way that that's done is there is an equivalent amount of feet associated with each fitting. So when I show you the chart, it'll be a little bit more clear, but basically there's a value for a 90-degree elbow, a value for a T, a value for a 45-degree elbow, and we're going to figure that out right now. So take a look at this chart. This is on page 103 in your textbook, and it shows that the friction losses are very small generally. So here we have a friction loss for a 3/4 inch 90-degree elbow. Here's the copper side, here's the cast bronze side. So 3/4 inch 90, we would find the pipe size here, and then we would cruise across until we found the 90-degree elbow, and it's equivalent to 1 foot of pipe. So that's going to be very little friction loss. But do take a note here that cast bronze over here on this side is much rougher surface than wrought copper is, which creates a higher PSI loss. So for example, here in a 90-degree elbow, that's 3 inch, it's the same as 18 feet, whereas in a wrought copper, it's only 5 feet. So keep that in mind. So now we're going to break down each component in this system to figure out how much PSI loss we're going to have due to friction and elevation, and how much PSI we're going to have left to work with. So one thing I want to point out about this chapter in particular is that in the Rainbird textbook, they go from one calculation to another without a clear explanation of why they're doing it. So over the period of time that I've been teaching this class, I've decided that I would rather continue to show you how to do it correctly using those 3 rules rather than following along with the catalog where they shifted gears with no explanation. So I'm also trying to be flexible. So what you're going to notice is that if you were to do the exercise in the book, that the solutions would be different in the back of the book than what we're going to be coming up with right here. So basically, we're going to continue using the 10 gallons a minute that we came up with by using the 3 rules. And what's different is they have switched the numbers from using 3/4 inch to using 1 1/4. So we're going to keep the 10 gallons, but we're going to move to the 1 1/4 copper. So here we go. So at our city main, right here, we have 111 PSI. Now we're going to walk through each component to see how much we lose. And then we'll backtrack, add them all together, and figure out what we have at the end. So here's component 1, and what component 1 is it's 6 feet of 1 1/4 copper type K pipe. This chart is from page 29 in the book, so if you need a larger, more blown up copy, you might want to flip open to that page really quick. And so remember when we talked about in chapter 1 is that friction loss charts for pipe are always in 100-foot increments. So they do that because imagine the decimal locations they would need if it was only by the foot. So keep that in mind that in this particular case, the friction loss at 10 gallons a minute for 1 1/4 pipe for 100 feet is 1.18. So it's a pretty small number. Now we're not going 100 feet, we're only going 6 feet. So this is where you have to remember your percentages and decimal point places. So remember when you're changing from a percentage to a decimal that you move your decimal point over 2 spots. So we have a 6-foot length that we need to figure out, and we have this information which is in 100-foot increments. So because 6 feet is 6% of 100, we're going to multiply it times 0.06. So our loss per 100 is 1.18 according to this chart, times 0.06 is going to get us a PSI loss of 0.0708. So that's the first number we're going to keep track of, besides our beginning pressure of 111. Component number 2 is this 1 1/4 wrought copper elbow. Again, we're going to be using 10 gallons a minute to figure out the equivalent pipe length for friction loss. So if you remember this chart earlier, here we have an 1¼ inch copper pipe. It's a 90-degree bend. It's equivalent to 2 feet of pipe. Well, here's our 1.18 per 100, which boils down to 0.0118 per foot. So that times 2 would come up to 0.0236 psi loss for this elbow. So you can see it's very minimal. Component number 3 is some more 1¼ inch copper type K pipe right here. So because we're going 3 feet, that's different than when we went 6 feet earlier. So it's going to be half the loss that we lost right here. So if 6 feet was 0.0708, then 3 feet would lose half as much, and the loss would be 0.0354. Now another thing you got to keep in mind is whenever you're going uphill or downhill, there's going to be a change in pressure due to elevation, losses, or gains. Well, because we're going uphill, we're going to be losing it. And we're going uphill 3 feet. So if you remember in chapter 1, I told you to always remember this number of 0.433, that we'd be using it throughout the semester. Well, this is one of those times. So we're going uphill 3 feet times 0.433. So our loss is going to be 1.299. So we're going to be keeping track of these numbers, and we'll be revisiting this later. Component number 4 is the same component as we had at component number 2. So it's basically a duplicate. We're going to lose the same PSI that we lost in this elbow as we lost in this elbow down here. And component number 5 is the same as component number 3. So its losses are going to be the same for friction, only this time there's no elevation to calculate. So component 6 is an 1¼ bronze gate valve. This is a chart that can be found on page 31 if you need to look at a larger copy. So now we need to take a look at your flow right here, find our 10 gallons per minute, scoot over until we find an 1¼ inch bronze gate valve, and note what the PSI loss is. Very minimal at 0.01. Component 7 is a 3/4 inch water meter. Here we have a chart from page 31 in the Rainbird textbook that shows pressure loss through water meters. We know that our flow is 10 gallons a minute and our meter is 3/4 inch. So we find our flow down in this column, we travel over to the 3/4 inch meter, and we see what our losses are. Component 8 is a 1 inch bronze gate valve. So again, here's our chart for bronze gate valves. We find our flow rate of 10 gallons per minute, scoot over till we find 1 inch, and we see that the loss through a 1 inch bronze gate valve is 0.03. So here we have component 9, which is basically our point of connection, where we're going to be taking off and starting our system. So we need to subtract all of the friction and elevation losses from our beginning pressure, our static pressure, to come up with our dynamic pressure. So here I've illustrated in a chart all of the losses that we had from component 1 all the way through component 8. We have component 1, which was 6 feet of 1¼ inch copper pipe. We have a copper elbow, 3 feet of copper pipe. Then we had our elevation change of 3 feet, another 1¼ inch copper elbow, 3 feet of 1¼ inch pipe, an 1¼ inch bronze gate valve, a 3/4 inch water meter, a 1 inch bronze gate valve, and after you subtract all of those losses from our beginning pressure of 111 psi, our remaining pressure is 107.872. So as you can see from that last chart in this exercise, that every little component has some sort of friction loss value to it. And if you do the system correctly, those numbers should be little, not big.